Hey all, this is Derek, and this is part 2 of section 3.3, and this will be absolute value inequalities, solving them both graphically and algebraically. So there's these couple of boxes that are going to explain how to do a less than or less than equals to inequality and how to do a greater than equals to inequality. To me, these boxes make no sense without the picture. And so again, while graphing isn't really a practical method necessarily for solving these most of the time, it really helps make sense as to why this one, the stuff in the absolute value is going to set up between the C's, and why the thing on the end here, and why in the second version is going to set up on the outside edges. And so what we're going to see is for these less thans, these are, other than if there's a sneaky negative sign, the less thans are always going to have solution sets that are going to kind of be within like this, and then the greater thans are always going to have solution sets that are going to go that way. Again, with a graph, it will make more sense why this is happening. And then let me do this setup with actual problems, and it'll be clearer. Okay, so for this first example, we got absolute value of x minus 1 is less than 3. So what I'm going to do is I'm going to graph y equals absolute value of x minus 1 and y equals 3, and then I'll work out the less than part. But let me get the boundary set up. So y is this, so this is going to be minus 1 on the inside, it's going to go right 1. So yeah, something like that. Hi, Eleanor. Ellie's saying hi. And then y equals 3, that's going to be right here. That's this line. So then what is this actually, what is this actually asking for? This is asking for, where is this function? Where is this function right here going to be less than 3? And if you look, it's everywhere below the line, right? So that right there, that's all the places that the function is under 3. And so my solution set is going to be x's, right? Because we're solving for the set of x's that make this true. It's gonna, there's no equal, so it's gonna go from -2 to 4. So that red line there, that's my solution set of x's. And that's what I was saying back over here, where all of these less thans are going to end up in between, because what we'll be finding is, unless there's a negative in front, which there won't be, but what we'll be finding is the part that is under the solution, under the line. So to write this as an answer, we would go from -2 to 4. Okay, so then back here, algebraically, when we have absolute value is less than something C, what it does is it sets it in between those two values. So we're saying this stuff has to be bigger than -C, but stays smaller than +C. So it's essentially staying between them. So for this, we're saying this x minus 1 here, whatever's going to make this true has to make it come out between the 3's, because that's where it's going to be less than. And so you can see if I just add the 1 everywhere, I get -2 is less than x is less than 4, which is much easier than doing all this drawing and stuff. But the reason that we're setting this up between the 3's is because we're looking for where is this function going to be below the 3's, or stay below 3. So for this next one, I wrote them out just as they're separate functions again. This time it's a greater than, so it's going to look a little different. For our y equals 2, that's right there. And then this would be -1 went right 1 and down 3. So that's right there. Just draw that out. So now, since this is a greater than or equals to, we're looking for where is this function greater than or equal to 2. So that's going to happen out here and out there, right? That's all the places where when I put in these values of x, like if I put in 7 minus 1 is 6 minus 3 is 4, that's greater than 2. So this is going to represent all the x values where I can get that are going to make this true. So we'd have solid dot going that way. And here we'll have, again, solid on the endpoint because of the equals and going that way. So our solution set would look like from negative infinity up to negative 4. And that'll be a bracket because of the solid. And then from 6 out to infinity. If I solve this algebraically, so that's where this is saying absolute value is either going to be less than the negative, so this way, less than the negative, or the absolute value is going to be greater than the positive. But the reason for that is, again, because when we look at the geometry, we have our absolute value. Where is it bigger than 2? All through here is bigger than 2. All throughout here is bigger than 2. So that's our solution. So we're going to do that same exact thing here. Oops, before we do that, sorry. The thing we got to do first is add the 3. So we always want to isolate that absolute value before we start splitting stuff up. So we want to get it down to one of those two forms there. So that gives us x minus 1 is greater than or equal to 5. And now either x minus 1 is going to be less than or equal to negative 5 because it's going to be under the negative, or x minus 1 is going to be greater than or equal to positive 5 because it's going to be greater than the positive. And then this 1 is kind of giving us these shifts. So we'll plus the 1 to both sides. And here we get x is less than negative 4. That's what we got right there. Or, so that'd be a union. X is greater than or equal to 6. And that's what we got right there. Okay, so for number 9, this one we're not trying to graph, we're just trying to solve. And you can see graphing this would not be that pleasant, so that's where having the algebraic method is totally good. So let's get the absolute value by itself. So add that 26 to both sides. So that gives us 7, and then 2k minus 1 greater than or equal to 21. That is convenient. So we'll divide out the 7 there. And 2k minus 1 equals 3. Oops, sorry. Absolute value 2k minus 1 greater than or equal to 3. So it is a greater than, so that means it's the kind that's going to set up like this. So we're going to do less than the negative or greater than the positive. So 2k minus 1 is either going to be less than or equal to negative 3, or 2k minus 1 is going to be greater than or equal to positive 3. So adding this 1 over, and 2k equals negative 2, divide the 2 on both sides, just keep writing equals, and k is less than or equal to negative 1. And then over here we'll go plus 1, 2k equals greater than or equal to 4, and then k greater than or equal to 2. So in interval notation, if it helps, think of the graph. And if you want to check yourself, just throw it on a number line, and it should look like that. So k is less than or equal to negative 1, so that would be going that way. Greater than or equal to 2, that's going that way, so that looks the right way. And so that would be negative infinity to negative 1 with a bracket, and then union 2 to infinity. So these next two basically look the same, but these are the ones that do funky stuff. So these are kind of the exceptions. So here I go to solve just like I did on the last one, minus 26 on both sides. And we got 5, 9k minus 1. And then this is going to be greater than or equal to negative 20. Again, if you see a negative on the right-hand side of these things, be suspicious. Let me finish it to here. So I got my absolute value isolated. So minus 20 divided by 5 would be a minus 4. So if we think about the graph of this, 9k minus 1, so that's got some kind of weird compression going on, which could also look like a vertical stretch, and a shift, but it's a horizontal shift. It hasn't shifted up or down at all. So this would be something like that. So when is this thing greater than negative 4? Well, pretty much always, right? Because this thing is, its lowest point would be at 0, at 1/9 actually. And it never reaches a negative value. And so anything I put in here for this k, when I take the absolute value, at worst it's going to be 0 or it'll be positive. It will always be greater than -4. So this is an example of all real numbers or infinite solutions. Okay, and then for this last one, we're going to subtract the 16 over. And that's going to give us 3, absolute value 10m minus 3. And it's going to be less than -12. Divide out the 3 on both sides. So now I have the absolute value of 10m minus 3 is less than -4. And so this is asking, when is this absolute value going to be less than negative? So if you think of what this would look like, we got a little graph. Again, this would be kind of some sort of V shifted. -4, that's down here. So when is it less than that? That's a never, because it's never going to get below -4, because this is always 0 or positive. So that would be a DNE.